All right, in this last video, we're going to focus on the Desmos parts of the chapter. So the first part of that is, can you just solve a quadratic equation by graphing? You might remember there's two ways to do this. One of the ways involves typing in two different functions and looking to see where they intersect. And the other method involves moving everything over to one side and then just looking to see where the one graph touches the x-axis at. So for number 32 here, it's already kind of been taken care of for us because one side of the equation is already 0. That means there's only one function to type into Desmos. So you don't have to type in the equals 0 part. You just type in the negative 16x squared plus 56x minus 10. And I put here y equals that negative 16x squared plus 56x minus 10 because I just wanted to make sure that it would graph, right? So if we turn that one on, you can see the parabola. In fact, if you zoom out a little bit with a touch screen here, it's pretty easy to zoom. You can see that this graph touches 0 at two different places. So both of those two places are going to be solutions, right? So the first one's going to be 0.19 and the other one's going to be 3.31. Since it says to round to two decimal places. So 0.19 and 3.31. All right. Now for the second one, not everything is on one side, right? So I'm going to continue with that solution method for the first two, and then for the second two, I'll use the other solution method. So I'm going to go ahead and move these two things over really quick. So I'm going to add 9x squared on this side, and I'm going to add 14. That'll cancel everything out on that side. And on the other side, I'm also going to add 9x squared and add 14. So that would give me 10x squared plus 14x plus 7. All right, so I'm just going to type in the one side of this equation. So 10x squared plus 14x plus 7. So y equals 10x squared plus 14x plus 7. Now remember, we're just looking for where does this graph touch the x-axis at, because that's where this graph would be equal to 0 at. Since this graph never dips low enough to touch the x-axis, that means that there's no real solutions to this. But now that we know about complex numbers, there are solutions, but they're just not going to show up on the graph because they're going to be imaginary numbers. They're going to be complex solutions. So instead of writing no solution on this one, up in the directions I say just write two imaginary solutions. That's really a better version of the answer because there are solutions. We just can't find them by graphing. All right, for 34 and 35, I'm going to switch to method 1, switch back over to the other method, and that is we're going to type each of the sides of this equation in as if it's its own equation. So we're going to type in y equals negative 29x squared as its own equation, and we're going to type in y equals 20x squared plus 56x plus 16 as its own equation. And we're just going to see where these two things intersect, if they do. So let's start off with y equals negative 29x squared. We get that kind of a parabola. And then for the second one, y equals 20, 56, and 16. So 20x squared plus 56x plus 16. All right, now these ones are kind of interesting. It's kind of hard to tell if they're touching. Kind of looks like they are. So you just kind of zoom in on that place and put your mouse there. Now it's not actually telling us that it intersects, which is kind of weird. So this might be one of those ones where it's better to solve it using a different method. So let's go ahead and switch over back to the other method. Let's move everything over to one side, which in this case we just have to move one piece. We just have to move this negative 29x squared over by adding 29x squared. So it's not that hard to do. This side will give us a 0. Over here we'll have 49x squared plus 56x plus 16. All right, so we'll just go change that. We don't need this one anymore. and we'll just go change this to 49. All right, this makes it a little bit easier to see. We're looking for where does this graph touch the x-axis at. It looks like it does, and when you click on it, it brings up that little gray dot there that shows, yes, this graph does actually hit the x-axis at the value of negative 0.57. So sometimes that's going to happen on Desmos where, for whatever reason, Desmos doesn't register that intersection point. So if you ever have a situation like that where it looks like they intersect, but it's not showing you that intersection, you might want to switch over to the other method and see if you can get a better answer. All right, for number 35, let's once again try the method number 1 where you type in one side as its own function and the other side as its own function, all right? And I don't really want to mess with adding fractions together. So y equals 1/3 x squared. Let's go y equals 1/3 x squared plus 6x plus 7. 6, 7. And then y equals negative 2/7 x squared minus 8x plus 11. All right. All right, I'm going to hit the home button over here. If you guys don't know where this home button is, this will get you back to a pretty normal view if you've zoomed in or zoomed out or whatever. All right, so let's zoom out here. We've got a couple parabolas. Looks like they touch in 2 different places. And you got to be careful here. You don't want to hit the y-intercept or the x-intercept. You want to get the intersection point. So we got there. That would be 0.28. And then if we move over here and check this one, that'd be negative 22.90. All right. So as you can see, both methods will work usually, but that one for number 34 was kind of weird with Desmos. So just be able to do both methods, and then if one method doesn't work for some reason, at least you can switch over. All right, now we're going to finish up with the applications here. And so the first application is all about projectile motion. All right, and in this question, they just give you the equation. They don't even make you create it yourself, right? So from 4 feet above the ground, Maya throws a ball upward with a velocity of 18 feet per second. So you'll notice the 4 feet above the ground, that's its starting height. So that's the ending of the equation there. The initial velocity, vertical velocity, is 18. So that goes right in the middle. And then because we're dealing with feet, the number in front here is negative 16. So this question really doesn't get any easier than this. You just have to go to Desmos, type in that equation. You can even type that equation in exactly the way it looks with h and t and all that stuff. So negative 16t squared plus 18t plus 4. Once again, I'm going to hit the home button over here. All right. And I'm going to zoom this out to make it look a little bit nicer. All right, so we can see this thing is traveling upward from a height of 4. So it's starting right here at time equals 0 and at a height of 4, moving upward until it reaches its maximum height. The maximum height is 9.0625, and it happens 0.5625 seconds after it went up into the air. And then we can see here that it's actually coming back to the ground after 1.31 seconds. So as you look at the questions that get asked on the test and get asked on this review, most of them are going to revolve around when it hits the ground, so the x-intercept down here, when it reaches its maximum, so the vertex up here, or something like that. So the first question, what's the maximum height the ball will reach? Looking at the vertex again, 9.0625. It doesn't say we can round it off, but you can usually round it off to 1 decimal place or 2 decimal place. So we'll go 9.06 feet. Then it asks after how many seconds will it reach that height. That's just the other part of the vertex. The x value here represents time. So 0.56 seconds. It only takes it 0.56 seconds to reach the maximum. And then finally, in total, how many seconds was the ball in the air? Once again, that comes back to when does the ball hit the ground? So we can see here that the ball hits the ground after 1.32 seconds. So this question on the test is going to be pretty standard like that. You're just looking for maximum heights or when does it hit the ground or something like that. All right, now these last two questions, they're going to be focused on the area applications. Both of these have something to do with area. Both of them are a little bit different from each other. And then we're going to skip 39. So I'm just going to show you how to do 37 and 38 to help you prepare for this type of question on the test. All right, so 37 says a farmer has 120 feet of fencing to make a rectangular corral around the side of his barn, or sorry, against the side of his barn. One of the sides of the corral will be the wall of the barn, but the other three sides will be created by the fencing. So the first step is to kind of get a visual on this, right? So a corral is just like a, like a place to keep horses or cows or whatever. So we're just basically fencing in an area of the grass or something. So let's say that this represents the barn. So he's going to use the barn as one side of his corral, but then he's going to use fencing for the other three sides. It's going to be a rectangular corral. So that means we will have two sides that are the same, the left and right sides here, and then potentially one side that is different. It could be the same. We could make it a square, but it doesn't have to be a square. All right. So part B says, so that's a good enough picture. So part B says, let X represent either the length or the width of the rectangle, whatever you want. All right. I'm going to go ahead and let X represent this one right here. All right. So now it says, devise an expression using X to represent the other side of the rectangle. So that would be this side right here. Now I'm going to go ahead and call that side Y right now, because at the moment we don't know if this side right here is going to be the same as this side, if it's going to be double that side. Like, we don't know anything about it. So technically it's another variable. It's a new unknown. What we're supposed to do is figure out how to write Y in terms of X. So this is something that we kind of learned in the first chapter. Being able to use another relationship that exists in order to change one variable into another variable. So here's the relationship we know. We know that the farmer has 120 feet of fencing. So the three sides of this corral, that would be the X, the Y, and the other X, those three sides have to equal 120 feet of fencing. So we can say that X plus Y has to equal that 120. And that means that 2X plus Y would have to equal 120. Now, we can solve this equation for Y by moving the 2X over to the other side. So that would give us, we would move it over by subtraction. So that would give us Y equals 120 minus 2X. And why is this important? Because when you have two variables, you usually can't solve anything. You can't figure anything out. But instead of using Y as this side length here, if we like substitute that out and we call this side length 120 minus 2X, now we just have one variable, and we can do a lot more and we can solve a lot more if we only have one variable. So that Y value is going to be equal to 120 minus 2X. So that's kind of the answer for part B. Now part C is where we actually do the important work. It says use your answer from part B to find the length and width that will maximize the area inside the corral. So basically this farmer is going to choose an X value, and then by choosing that X value, he wants to get the biggest amount of space he can in his corral. So in order to do that, we need to write an area equation. Well, area of a rectangle is very simple. It's length times width, or it's base times height, right? However you like to think of it. The base of this rectangle is going to be this 120 minus 2x side length. All right, so that's our base. And then the height of the rectangle is just simply going to be this x side length. That's the height. So our equation is area equals 120 minus 2x times x. And that's an equation that we can go and type into Desmos. If we let the area be represented by the y variable, we can just go type in y equals parenthesis 120 minus 2x times x. So let's go see what it gives us if we type that in. All right, that's given us a pretty big graph here, so we're going to have to zoom out. Oh, that didn't work. Let's see. Oh, okay, so we got a big graph here. Now this graph represents area because our y value is area here. So if we kind of zoom this to the right place, we can see this just creates a really nice parabola, and this parabola has a maximum on it. So if we go ahead and click there, what this maximum tells us is that an x value of 30 would create a y value of 18. Now in our equation, the x value represents this side length of the barn, and the y value represents the area. So by finding this vertex, it's basically saying to us, hey, if you choose an x value of 30, it will give you the largest possible area, and that area will be 1,800 square feet. So that means that our height of the rectangle, or if you want to call it the length of the rectangle, that would have to be 30. So one of the dimensions would be 30 feet. And then the other dimension we can solve by plugging that 30 in to our expression here. So 120 minus 2x. So 120 minus 2 times 30, that's 120 minus 60. That tells us that the other side will be 60 feet. So if the farmer chooses the side lengths of his rectangle to be 30 by 60, that will give him the greatest area inside his corral. All right, now number 38 still has to do with area, but this question is going to be a little bit different. We don't have to do so much creative thinking with this question, but we still got to be able to draw a picture, model the situation. We're still going to have to create an equation, and then we're still going to use Desmos to help us solve. So it says your company is cutting steel rectangular frames as part of a new product that they are launching. The frame is going to go around a 6 centimeter by 11 centimeter rectangular area, and it will have a uniform width all the way around. And then a lot of times with manufacturing, like, you have very specific specifications that you have to fit. So for this one, in order to keep the weight down, we're going to make the area of the frame, just the frame, 28 centimeters squared. All right. So let's draw a quick picture to represent this. All right. So we've got a 6 by 11 rectangular area. So 6 and 11. And then we're going to be putting a steel frame around the outside of that. And it's going to have a uniform width. All right, so this is kind of the idea here, right? We know that the frame itself, so just the outside part, is going to be 28 centimeters squared. And then we can calculate the inner part because it's a rectangle of 6 and 11. So the area inside here would be 66 centimeters squared. All right. Now we can obviously add those two values together. So 28 plus 66, that would give us 94. So 94 centimeters squared represents basically the area of all of it. So the inner area and the frame area put together. All right, so let's go to part B. Part B says let X represent the width of the frame. So we're going to say all the way around the edge here, everywhere around here, this length or this width right here is X. All right. Now we need to create an equation involving area that can be used to solve for the value of x. Now you can do this in a couple different ways, but one way is going to be a lot faster and a lot easier, so that's the way I'm going to show. I'm not saying there's no other way to solve this, but this is kind of the faster way. Because the frame, in order to find the area of just the frame, we would have to cut this up into a bunch of pieces, right? Like you'd have to maybe make a cut here to create a rectangle, figure out what that area is, maybe make a cut here and here. You'd have to add up multiple areas to get that 28 centimeters squared. If you want to do that, that's fine. But I tend to solve these questions thinking about the whole area altogether. So all I do is I just think about what's the new base and what's the new height of this rectangular area. The inner part is 6 by 11, but what's the total base length and the total height length? So for the base length here, the inner part is 11, and then we're basically just adding on a length of x to both sides of that 11. So we're doing 11 plus x, which could be represented as 11 plus 2x. And then the same thing is happening if you look at the height of the rectangle. The inner height is 6, but then we're adding a value of x, or a length of x up here and a length of x down here. So we're adding 2 x's on to that 6. So in both directions, we're just adding on 2x to what was existing. And now we can calculate the area of this entire product. All right. So we know that area of a rectangle is always equal to base times height. So the base is 11 plus 2x. The height is 6 plus 2x. And in this case, we actually know the area because we already calculated over here. The total area is 94. So this whole thing is going to be equal to 94. Now that is the equation that we're going to have to solve in Desmos. So let's bring it down here. I'm going to go ahead and switch the sides of it. All right, now you can solve this using method 1, where you type in the left side of the equation as its own function, and you type in the right side of the equation as its own function. But I don't like to do that in this way because I don't like to have to go searching around for where my answer is on the graph. So instead, I'm just going to very quickly move this 94 over to the other side. Just subtract the 94 and subtract the 94. You don't have to simplify, you don't have to FOIL, you don't have to do any of that. Just leave it as 11 plus 2x times 6 plus 2x, and then just simply subtract that 94 on the outside. Now we can just type in the left side of this equation and then check to see where it equals 0, which would be the x-axis. So we'll start off with 11 plus 2x and then times 6 plus 2x, and then we'll subtract away that 94. I'll zoom back in a little bit here. We get a nice parabola coming in at 2 places on the x-axis, which is where it equals 0 at. And since this is a physical, real-world problem, this solution over here that's negative isn't going to have any real-world significance. You can't make the width of the frame -9 anything, really. So really, the positive side is the one we want. So 0.76. So x in this case would equal 0.76. But in the context of the problem, what does x stand for? It stands for the width, right? And since we're measuring in centimeters, the width of the frame needs to be 0.76 centimeters to keep within the specifications that the engineers gave us. So the question you see on the test is going to be, somewhat similar to this. You're going to need to draw a picture. You're going to need to set up an equation. The equation will look pretty similar to this, area equals base times height. The only differences might be, is it getting added onto all 4 sides? Maybe it's only getting added on 2 or 3 sides or something like that. So just pay attention to the details, but if you can draw a picture, that'll help you write the equation. Once you write the equation, it's just solving an equation using Desmos.